Hello, can everyone hear me? Okay, perfect. Hello, my name is Lori Tan. I'm a graduate student in the Bernardi group, and today I'll be talking about spin orbit coupling and spin relaxation times using Perturbo. Spin relaxation due to phonons are important for many spin-based applications. For spin transport, spin relaxation affects the preservation of spins over long distances. In spintronic devices, spin relaxation affects the efficiency and device performance. And for spin-based qubits, long spin relaxation times are important for performing complex quantum operations. Spin relaxation from phonons sets an intrinsic limit for a wide range of temperatures, and understanding the relationship between spins and phonons are important for advancing these fields. Here is the workflow for Perturbo that we've seen in many past presentations, where we get the ground state energies and wave functions from DFT, the phonon perturbation potentials from DFPT, the Maxwell localized Wannier functions from Wannier 90, all of which we use to compute the electron-phonon coupling matrix elements, G, which we then use to compute quantities important for transport. We can add spin-orbit coupling into this framework by using fully relativistic pseudopotentials for our DFT and DFPT steps, as well as specifying spinor-related variables in our Wannier 90 step. By using routines within Perturbo, we can then compute spin relaxation times, and we'll learn how to do that today in the hands-on session. So spin-orbit coupling can be very complex. On the right here, we have the visualization of Dresselhaus spin-orbit coupling in 3-5 type semiconductors. When we include spin-orbit coupling into our electron-phonon interactions, our G electron-phonon coupling matrix element, the wave functions become two-component spinors, and the phonon perturbation potential becomes a 2x2 matrix. So the general workflow is for including spin-orbit coupling is using fully relativistic pseudopotentials for our DFT and DFPT step for our electrons and phonons. And then we perform a rotation and interpolation of these electron-phonon matrix elements using crystal and SU2 symmetry. So first, we directly compute the matrix elements in the irreducible wedge of the Brion zone. And then we can fold out these matrix elements using symmetry operations to the full Brion zone. So we use both rotations in space, like we use O3 group and SU2 group to rotate the matrix elements. And it's very important that we use the SU2 group, which allows us to do rotations in spin space. Without this rotation, it would lead to uncontrolled errors. We use this in Perturbo, and we can accurately compute these electron-phonon interactions with spin-orbit coupling. So next, we can take this a step further to computing spin relaxation times. To compute spin relaxation times, we need what's called the spin flip matrix element. So here we have a side-by-side comparison of our regular electron-phonon matrix element that we've seen previously and our spin flip electron-phonon matrix element. So on the left, we have G, which captures the probability of scattering from initial block state to final block state, and has the phonon perturbation potential. And for this electron-phonon matrix element, we can choose to include spin-orbit coupling or not, and this captures the strength of scattering. On the right, for the spin-flip matrix element, we must include spin-orbit coupling, and this applies primarily to centrosymmetric materials. In centrosymmetric materials, we can write our block states as effective up and down states that diagonalize the spin operator. And here in our spin flip matrix element, It captures the probability of scattering from initial block state to final block state with opposite effective spin, which is the key difference between the regular electron phonon matrix element and the spin flip matrix element. So to compute spin relaxation times from first principles, we have our spin flip matrix element, and in centrosymmetric materials, the primary mechanism for spin relaxation is the Elliott-Yaffe mechanism, where spins can relax due to electron phonon or electron defect interactions. Around room temperature, phonons are most dominant. So here we have the spin relaxation time due to the Elliott-Yaffe, since we're studying centrosymmetric materials. Here we have the phonon occupations, electron energies, and phonon frequencies, all computed from first principles. And here we have our spin flip matrix element discussed earlier. On the right here, we have the spin relaxation times of silicon, thermally averaged over, or shown for a range of temperatures, and we see very good agreement with experiment. Today, we will be computing on diamond in the hands-on. So there are several new spin features available in the latest Perturbo release. Some things to note is when using these features, some spinner-related variables must be specified when generating the EPR file. There are 4 new spin-related calc modes available for you to use that come with plotting feature support from Perturbo-Pi. So now, in Perturbo, we can compute the spin flip electron phonon matrix element, the spin texture, as well as the spin lifetimes. So we may have seen from earlier hands-on that we can compute the regular electron phonon matrix element. Here, we use calc mode fmat spin to compute this spin flip matrix element over bands given 2 lists of K and Q points. The general workflow is we run our fmat spin calculation, which is a fairly fast calculation. This then generates the YAML file, which we then post-process using Perturbo-Pi. And here on the right is the phonon dispersion of diamond overlaid with a color map of the spin flip matrix elements. And we can see that certain regions of the certain phonon modes have stronger spin flip matrix elements than others. We can then compute the spin texture. So this is the spin expectation value for sigma z. This is the calc mode spins. So you will provide a list of K points, and then we'll get the spin texture over the bands. So the general workflow is we run a spins calculation, which is also a fairly fast calculation, which then produces a YAML file, which we then process using Perturbo-Pi. Here, the band structure is overlaid with a color map of the spin expectation value. We can plot this using a linear or log scale. One thing to note, this is 1 minus the spin expectation value, which is why it goes from 2 to 0. So the ends of this color map are when the ends of this color bar are when these spins have the same direction, and in the center, or 1, is when the spins are opposite. Finally, we can compute spin lifetimes. So there are 2 calc modes that are relevant here. Similar to how we use the regular I'm sigma or imaginary self-energy for regular relaxation times, we have a spin version. So the calc mode is I'm sigma spin, which computes the imaginary self-energy for the spin flip process for states in a set of given bands with a specified crystal momenta. We can then use calc mode spin lifetime, which computes the spin lifetime for the given temperature, chemical potential, and carrier concentration. So the general workflow, which we'll go through, is running a setup calculation, which we saw earlier in Kelly's presentation. And then we run the imaginary M sigma spin. and then we run the spin lifetime calculation. We'll do a post-processing step with VM sigma spin to visualize whether or not the calculations converged. And then we can look at the outputs for the spin lifetime calculation. So now we will go on to our hands-on session. Exit. Okay. Can everyone see my screen okay? Hopefully. Okay, perfect. Okay, so to start, we have the hands-on 6 tutorial from the GitHub titled Spin Relaxation Times. So you can download the materials from the box link, or you can just use the materials from the GitHub. Our first step, as we've seen in previous tutorials, is to set up the Docker environment. So I have the command already set here. I have the command set here. So again, Docker run, my volume is my working directory, and then I have the directory in the Docker container. And then I'm using GCC OpenMP. So now we're in the Docker environment. You can set OpenMP commands if you would like. Most of the calculations are fast, except using the imaginary self-energy calculation. That is the most expensive calculation. But you can also run it serially, and in today's example, we set the parameters so it doesn't take as long. So for the EPR file, there are 2 options. Option 1 is generating the EPR file from the Quantum Espresso inputs. Since there are additional spinner-related variables, and we've learned from previous hands-on how to generate the EPR file, if you'd like, you can generate it from scratch using the provided inputs. We will not be going over that today for the sake of time. We will be using the pre-existing EPR file, which you can find in this link in the box. Alternatively, if you're just in the regular box link, you can navigate to hands-on 6, the diamond folder, and then you go to QE to PERT, and then references. This is where the EPR H5 file is. So please download the file, and then we'll move it into our work folder. So I have the download here, and I have my volume here. This is another way you can move folders into the Docker. So we'll navigate. So on the right, we have my Docker volume, and it will navigate to the Perturbo folder. So we see all these other folders. I'm just gonna drag and move my EPR file that I've previously downloaded there. And if I go to the folder that I moved it in, so I'm going to hands-on 6, see diamond, go to Perturbo folder. I see the EPR file here. Okay, so to start with, we will also be creating soft links to this file throughout the tutorial. So first we'll go to the fmat spin directory, so pert fmat spin, and then inside, if we look inside, we will see a references folder with some results that you can compare to if you'd like, the kpoint input file, the qpoint input file, the pert input file, and the plotting script. So let's look at the input file, the Perturbo input file. So here we have our prefix diamond or diam. We've specified our calc mode, and we specified the K and Q list, as well as the band min and max. Here we've also specified the phonon frequency cutoff. I don't believe this is a required variable, but we can check the input generation if you'd like to see. But we can also see if what the K point and Q point files look like. So when we run these FMAT calculations, we generally run them for a chosen Q point as a function of, for a chosen K point as a function of Q point. So here we're just running it by setting the, just over the gamma point. So 0, 0, 0, and then we can look at the list of Q points that we're running it over. So this is just a list of Q points for diamond. Okay, so then we will soft link the EPR file from the previous directory. So we see another important thing is just when running these calculations, just making sure we have all the necessary inputs. So we have our EPR file, we have our K point file, Q point file, and then we're ready. So now we can run just turbo.x. We'll run this command, pert in out, so we can see the outputs, and it's working now. Okay, and we're done. It should be a fairly fast calculation, regardless if you're running it serially or parallelized. So if we look at the outputs, we see there are two new files that were created, this ASCII diam.flip as well as our YAML file. The Perturbo-py plotting script uses the YAML file here. So in the plotting script, we are importing Perturbo-py and we are creating an fmat spin object from the fmat spin class, and then we are plotting it. So if we run this command, Python 3 plot, okay. And then we will see now an image arise. And since I'm using a Windows computer, we can go to the Perturbo folder on my file directory, and we can see, we can open up the image. Okay, so the color scheme is a little hard to see. We're still working on updating Perturbo-py where you can customize the color maps, but here we can see the bands that are most that have the strongest spin flip electron phonon coupling matrix element for diamond. So great. Now we will continue moving on to the computing the spin texture. So if we go to, we're going to change folders. So now we're back here. We're going to go to the pert spins folder. And inside, we will see the references folder, the K point file, as well as the Perturbo input file. So if we look at the Perturbo input file, it's very minimal. This is very similar to a bands calculation where we specify K points, and that's pretty much the only thing we specify. Don't forget to soft link the EPR file. So the necessary inputs here are the K point list and the EPR file, and then now we can run Perturbo. I'm using this command. And we are running this over 16 bands, and it should be a fairly fast calculation. So now we see there are two new output files, diam.spins, as well as a diam.spins YAML file. If we open up our plotting script provided here, we see the we are creating a spins object using the spins YAML file. Something important to note here is that we are specifying this to be a linear to be plotted on a linear scale, so log equals false. If you'd like it to be plotted on a log scale, you can set log equals to true. I believe by default it is set to false, but we can check the API on the PerturboPy website. So if we run Python 3 plotting, okay, calculation's done. Now we have our new image here, which we can check. We can just open it up. So if we go here to our spins, we can open up the image. And we see our bands as well as the spin expectation value for each of the points on the bands. And we can see that for the lighter color regions, it's when the spins are both up. And for when the darker color region is when the spins are both down, since it's 1 minus the spin expectation value. These orange regions are when it's opposite spin. So great. So now we can see, we can go on to the spin relaxation times. So to run the spin relaxation times, we'll need to do 3 calculations. The first calculation is the setup calculation. So I'm going to change directories to Pert setup. So in here, I've already provided the temper file as well as the input file. So if we open the temper file, for today's hands-on, we are only running it for 1 temperature. We have the specified chemical potential, as well as the carrier concentration. As we've seen with previous hands-on, you can specify find E Fermi. So for a specified carrier concentration, it will find the Fermi energy, Fermi level. Alternatively, you could set it equal to false, and it will it will find the carrier concentration instead. So in our input file, we have our calc mode setup. Our K-grid is 80 by 80 by 80. This is the energy window we're specifying, and this is an EV. And we're doing this for bands 9 and 10. And we also have our temper file specified. So we can soft link our EPR file as the main step. So now this is all that's required in the setup calculation. So now we can run Perturbo.x. And this generates the grid for specified energy windows and temperatures. So here the calculation has finished. And we can see that there are 4 new files generated. 5 actually. Diam.dos, which is the density of states, diam.doping, which is the doping concentration, as well as the setup YAML file, which we won't really use. And then the diamtet.h5 as well as the diamtet.kpoint files are the most important ones for the remainder for the calculations coming for the next calculations. So we're all done with the setup calculation. So now we're going to change directories to the imaginary I'm sigma spin. So inside, we should see 2 files inside the folder, the input file as well as the plotting script. Let's look inside the input file. So it looks probably very similar to other imaginary in sigma calculations. So we specified the calc mode here with the spin here. Our K-list, FK-list, is the K-point file from our setup calculation. Our temper file is the same as before. We'll use the same temper file throughout this calculation. our band min and max are the same as our setup calculation. We've set the phone-on frequency cutoff to 3 and the delta smearing as 20. These parameters can be tweaked more to try to affect convergence and see if you're content with the resulting values. We're using Cauchy sampling, and one thing to note is that we're using quite a small number of Q points for the sake of time. Ideally, this would be a much larger sampling value to ensure convergence. So now we will copy over some files from our previous calculation. So Pert setup, the temper file, and then we'll also copy over the tet file. Okay, great. So now we see those there, and then we will soft link our EPR file. So now we can, you can run it as is. You can specify the OMP number of threads, or just use the default number on your computer. I will specify this. Ideally, you could specify this to the max number that's allowed for your computer to speed up the calculation. Let's see, and next. And while this calculation is running, I will be talking about the input files for the for running the Quantum Espresso, if you want to generate the EPR file from scratch. Okay, so this is running. So you can also use MPI parallelization for this step. It will be much, much faster. But I believe this calculation should take 3 minutes, hopefully not longer, but no worries. So if we scroll up to the top of our of the tutorial where we see how to generate this from just the first SCF step, to generate the EPR file, you need fully relativistic pseudopotentials, and then you also need to specify some more flags. So in your SCF step, there's a non-collinear and spin orbit flag that must be set to true, or else your calculation will throw an error. In the NSCF step, you also need to set these same flags to true. In the phone-on step, there are no additional spinner-related variables that need to be specified, just using the temp folder from the SCF step. In the Wannier 90 step, there's a flag called spinners that needs to be set to true. In the diam.win, or just a .win input file, and in your PW_1 input file, there's a right spin flag. So this outputs this is a very important flag. So it outputs a .spin file by specifying this flag, and we need this as an input for our QE to PERT step. So after getting all of these, after specifying all these flags and having this additional file, we can then run QE to PERT. So there are some additional flags that must be specified in QE to PERT as well. So this flag, lspinmat, must be set to true or else you won't be able to perform these spin calc modes in Perturbo.x. And as we saw yesterday, there are several files that need to be in the run directory, like centers, .centers.xyz, u.mat, as well as u.dismat for the run directory. We need to copy over this .spin file into our directory for QE to PERT so that, or else it won't run. And then just like before, we will copy over this temp directory, this XML and save folder from our NSCF calculation. And that's pretty much it to generate the EPR file. Are there any questions?
So in that process, like, what are things that like tend to go wrong, or things that you could like specifically look out for?
Okay, so the question was, what are things that could go wrong in this process? It's a good question. I think the workflow is fairly similar to generating a regular EPR file, just these additional flags. I think things that could go wrong, it's very important to have a very good Wannier interpolation. I think prioritizing that. I think the quality of your Wannier interpolation affects your spin relaxation times and your spin results. So I believe if you think your spin lifetimes that we eventually get are not as good of a quality as you would like, and you've increased your convergence on your imaginary self-energy calculation and it's still not looking great, I think the next thing you could question is your Wannier interpolation.
And these calculations, do they also capture the like RASPA kind of effect where your compound is non-centrosymmetric, so that you can have spin-orbit couplings, asymmetric spin-orbit coupling kind of stuff?
So that's a great question. So the question was, do these calculations capture RASPA effects as well as like non-centrosymmetric for non-centrosymmetric materials as well? Unfortunately, these calculations are like primarily and should only be used for centrosymmetric materials. I think for systems with these calculations aren't as effective for systems with like asymmetric systems because they're not as dominated by the LEFA mechanism, and also we can't decompose the block states as effectively. Okay, so my calculation finished. If other people need more time, please let me know in the chat. If not, we'll continue on. So this calculation took 5 minutes for only 10,000 Q points. Ideally, we would increase that by a few orders of magnitude, but that's okay for now. We can plot. Yeah. Can somebody read it out?
Yes. Okay, so 2 questions from. Sorry, I'll turn on my microphone. 2 questions from an anonymous attendee. One is how to generate the FK list and FQ list files. So maybe you could go over that first.
Okay, that's a great question. How to generate the FK and FQ list files. Let's go back to the setup calculation. FMAT calculation. So if we look at the how to generate, you can type this out. So this is in crystal coordinates. The number at the top is the number of entries, and the numbers, these like are the crystal coordinates here, and this is the number of points. I think a better example would be looking at the Q point file. So here we have 6 different coordinates listed here, and the number on the far right is the number of points per I guess crystal point. So if we look at the FMAT calculation, we'll see that these are fairly evenly spaced. And then since I specified 20 points, that's how many points will be between these 2 crystal coordinates I specified. And then this is 50, and then you have to specify 1 at the end so it doesn't throw an error. You can also have some more points after if you'd like. But that's how you generate the Q or K list. They both follow the same format, and you can choose whichever path is best for your system. This is the general format that they follow, and they also can be used, like, you can use them for interchangeably because it's all the same format. Was there another question?
Yeah, so the second question is it possible to calculate spin relaxation times due to mechanisms other than the Elliott-Yaffe mechanism?
For that is currently not implemented in Perturbo yet. There are definitely other spin mechanisms besides Elliott-Yaffe, but for Perturbo, this is the main mechanism that we're calculating. So to answer your question, for Perturbo, at this moment, no. Okay.
We're working on that for next time.
Yes, it hopefully will be in a future release to capture non-centrosymmetric spin relaxation mechanisms, as well as hopefully other effects. Do I have it? We do have it. We do have it. That is the work of member Jinsu Park, who is now a professor at in Korea. So that is future work. Okay, so now we are almost done with this hands-on actually. We go to, now we can plot our the results of our calculation. So we see the imaginary M sigma spin plotting script. So we're creating an object from the M sigma spin class, and we're using the YAML file as an input. Here, there are more details in the PerturboPy website, but here, since we only have two bands, band 9 and 10 in our calculation, they're just the first, only two bands on these key. So if I run this, work, great. Okay, let me So hopefully the image that you see, it might not be converged because we use such a few number of Q points, which is okay. We ideally would do this on a much larger number of Q points. So let's see if so it's not converged. We will still run the spin lifetime calculation, but on your own, you could run this on much larger sampling. Here is with 100,000 Q points, so it's much more converged compared to just using only 10,000. Actually, I believe I used a million Q points, and it's much faster when you use MP parallelization. So now we're on to our last step, which is the spin lifetime. So we're going to just change to that folder. So we will need certain files from the previous calculations. So we will copy over the temper file from the setup calculation, as well as the tet.h5, not the K point. H5 is a subtle distinction. Okay. And let's see. Actually, before I run this calculation, I realized I didn't talk about the outputs generated for this M sigma spin calculation. So there's actually quite a few files that are generated here. We have our M sigma flip calculation, but this calculation also generates the regular imaginary self-energy. We also have mode resolved M sigma flip and mode resolved for both the spin flip and the regular imaginary self-energies. And then we have our YAML file. So when we go to the spin lifetime calculation, we need to make sure we copy over the right one, the M sigma flip. I don't think the calculation will run if you don't have the correct file. So we have the temper file, we have the tet file, and we have the M sigma flip file. Now we will soft link our APR file. Okay, and then now we can run Perturbo. And this is a very fast this should be a very fast calculation. So okay. The input file for this calculation is also very simple. It's kind of looks very similar to the setup file, so there's not many variables to specify besides just using the same grid, using the same temper file, and using the same bands, min and max that you specified. Great. So we can open so there's no Perturbo-Pi support here since we're just getting a singular relaxation time since we only ran it for one temperature. So if we open the ASCII file, we can see these are thermally averaged. So we have our tau relaxation time in nanoseconds here, as well as the Fermi level. So ideally, what you would do is you would have your temper file with many more temperatures, and then you can see the trend for your material. Sorry, do you mind repeating that?
How do the two, like the imaginary about sigma and the spin lifetime calculations differ?
How do they? Okay, so the question was what's the difference between the regular M sigma flip and the regular M sigma and the M sigma flip?
No, M sigma flip and the spin lifetime.
Oh, what's the difference? Oh, so this one just computes, the spin lifetime just computes the scattering rates using the results of the M sigma flip. Is that?
Right, so you're just summing them.
Yeah, this is just thermally averaging using like a tetrahedron integration, just thermally averaging it for the temperature. Did that answer your question?
Yes.
Okay, sorry. Okay. And then you can also check the outputs in the YAML file. If we navigate to the bottom of the YAML file, we will see exactly what we saw in that other file, the number of configurations. So here we only specified one configuration, which is 300 Kelvin, and our temperature, our chemical potential, and then our resulting tau. Okay. Are there any questions?